Okay, in this video, we're going to start looking at data structures. Okay, so a data structure is a way of organizing data, usually with a set of operations that can be performed on them. For example, we might talk about something like a list, which would be a set of ordered items, or something like a set, which would just be a collection of objects, maybe a set of integers, for example. And then when we talk about some organization of data like that, we're going to want to implement operations. Like on a list, you might add things into the list in the middle, at the beginning, at the end, or you might remove something from your list, like a grocery list. Or for something like a set, you might want to do, you might want to ask, is an element in the set? Or you might want to perform a union on two sets, right? So there are operations that you'll want to perform on those data structures. And then when we think about how we organize and implement those data structures, then we're going to strive for efficiency in terms of the amount of compute time it would take to do the operation and the amount of memory used. Now, it turns out that the most common ways of organizing data boil down to a few key structures. One of them you already know well, that's the array. An array is just a contiguous block of memory. And arrays are really useful for representing things like strings or vectors, integer vectors. An array is a really helpful way for collecting things together in memory. Unfortunately, arrays are not good at everything. And so, that led to people looking at things like lists that are a little more flexible. And then, over time, we discovered many other structures like graphs, trees, and hash tables. And once you learn, what these several, structures are, it turns out that when you need a new data structure, you often can identify it as a combination of these, some new combination of these, a combination of arrays, lists, graph, trees, and hash tables. And these can be put together in lots of different ways, nested together in lots of different ways. And you might hear somebody say, well, somebody's already implemented these data structures once. Why do we need to learn them and do it again? Let's just reuse code that's out there. Well, the problem is that, when you start building software to solve some new problem, it's not that you just need an existing array, list, graph, or tree. You often need to tune them and customize them and merge them together in new ways that no one's done before. And then there's no code possibly that will do exactly what you want. And you have to implement these basic pieces yourself or draw from libraries that provide some of the implementation, but not a complete implementation. And then I also find in my own work that there are a lot of things we end up implementing that maybe aren't a list in the purest form or a graph in the purest form, but it shares enough similarity to a list, graph, tree, or hash table that having a good understanding of how they operate and what they are means you'll do a better job at implementing your new code. Okay, so these data structures are really fundamentally important. And when you understand them, it increases your understanding of code so much that you're going to be able to solve problems, new problems in ways that you didn't realize was possible before. Okay, so probably, the most basic data structure other than an array is a list. And a list is a common abstract data type for holding ordered data. And let me just comment about ordered here. When I say ordered, it can be any kind of order. It's not necessarily like a sorted order, like alphabetical order or numerical order from smallest to largest. It could be that, but it doesn't have to be that. It just is some ordering that matters, and we want to preserve that ordering that matters. For example, if I need to drive around town and go to 4 stores, then I might organize those stores in some way that makes sense to me. Like, I might know there's a particular way I like to drive around town, and then I could put those stores in a list in the order in which I want to visit them. And so that order is meaningful to me, but it might not be meaningful to anyone else. But in the context of a program, lists need to be able to hold data in an order that's meaningful to the program. And so when we talk about order, we just mean in the general sense that if I put things in the list in an order, it stays in that order and it won't suddenly change around. This is in contrast to some data structures which don't enforce order that we'll see later this semester. In fact, it's kind of easier to design structures that enforce order, right? An array kind of naturally enforces order because an array is a contiguous block of memory. And if I store things in memory in a certain order, they're going to stay in that order, right? So an array naturally imposes ordering, and a list is also going to naturally impose ordering. And then I want to do things like append data to my list, or I want to remove data from the list or search for something in the list. And a lot of the time here, I'm just going to call it an item, but that item could be an integer or a string or, you know, a double value, or, you know, it could be any other kind of data type we can invent. Like it could be any kind of object we can make in C++. That could be our item that we put in the list. So an example might be a grocery list. Being a dad and, you know, having a family, going to stores and grocery shopping is something, or at least before the pandemic, that I would, you know, do all the time. And even during the pandemic, we still had to do shopping. We just do it in a different way, right? And so we're often making some sort of list of things that we need. So maybe I need to buy milk, cereal, potato chips, coffee, and toothpaste at the grocery store. And I might make a list to represent that, and I might put them in my list in the order in which I'm going to walk around the store and buy them, based on, you know, how I know things are placed in the store. So things I would customarily want to do to a grocery list that I write down on paper is I want to be able to add things into that list. I want to be able to remove an item when I buy it. I want to be able to, you know, figure out what's the next item on my list that I haven't bought yet. Maybe I want to scan through my list and find something I think I put on my list, and check to make sure I did. So these are things we often want to do to a list. And certainly as humans, when we do this to a list, we might do it in a very flexible way. We're not really under many constraints, but when we implement it in code, then we have to be far more detailed about what these operations mean. And we'll get into some more detail about, you know, how they work and how you might implement them. A simple C++ object for a list might look like this. This is an incomplete class declaration. I'm just kind of sketching out what it might look like. So I might say I have a class called list, and then I might have a function append that adds an item to the end of my list. You know, this is kind of like having a sheet of paper where you just kind of go down the sheet of paper, adding things to the next line that's free. I might want to remove an item. And in this case, I'm referring to a very specific kind of removal where I'm just going to remove the top thing on the list. I'm not removing an arbitrary item, just, you know, the first thing, but later we'll come back and talk about removing, you know, an arbitrary thing from the list. I might want to know if my list is empty, because if it's empty, then I'm done if I'm shopping, right? Or if I'm making my list, if it's empty, then I need to work harder. Insert after might be like realizing, oh, when I'm on the aisle for ketchup, I should also get mustard because they're going to be placed next to each other. So maybe I want to, you know, insert mustard into my list right after ketchup. And this insert after function will let me do that. Okay, so this is what an object might look like. And then after declaring an object like this, you know, I would need to provide an implementation. But we can kind of ignore that implementation for now and just think of abstractly about how these things work. So let's pretend like the items that I'm dealing with are strings. That's nice because that matches well with my grocery list idea. And so when I create a new list object, what I would probably want is when I first create it, like using a default constructor, then that list is empty. And, you know, I'm just going to show this conceptually with, like, in set notation using empty braces. So there's nothing in my list. So I'm starting with an empty list. And then if I call my function empty, l.empty, then it should return true because there's nothing in the list. And then I can append eggs to my list. And so, you know, over here I'm showing that inside my list I just have eggs. Eggs is at the end of the list, which is also the front of the list because it's the only thing in it. And then I can append bread to my list, which means I'm going to put bread at the end after eggs. So now I have eggs and bread. And then if I call the remove function, remove, in this case, just removes the front of the list. And so it's going to remove the eggs and leave me with just bread. And then if I call empty one more time, then it will evaluate to false because I still have bread in my list. It's not empty. Okay, so that's kind of an example. And when we think about a list and when we look at operations happening on the list, you can kind of imagine this abstract idea of list. And that's actually how, we want programmers who would use our list object to think in this abstract way, to not worry about the underlying details of how the list really works, and just know that if they do these operations on the list, then they get this, they can imagine what's in the list as if they're writing it down on paper, and get the results they expect. Okay, but underneath, inside the class, there are multiple implementations we can possibly choose. And we'll talk about that in the next video. Okay, so in summary, a data structure is a way of organizing data, usually with a set of operations that can be formed on them. So here we looked at a list and what a list data type would be. It's a way of holding ordered data. And then the operations we often want to perform on a list are things like adding data to the list, removing data from the list, searching for an item in the list, possibly even like reading over our list. There are other operations you might think of, and they could be added here. This isn't an exhaustive list. It's just examples of things we typically want to do on a list. Okay, in the next video, we'll start talking about ways we might implement this list.